This week, we are going to be talking a little bit more about software and apps. And we're going to take a little bit of time to talk about how they are developed. Let me full screen this really quickly for you guys. A couple weeks ago, I put up a poll to see what you guys were interested in, and you guys voted to do it just this way. That is cool. We'll do the same thing next week, which will be on web development. So we're just going to go through what the PowerPoints have to offer. And there's going to be a quick demonstration on troubleshooting after the presentation, so please stick around after the PowerPoint is over. And so the first thing we want to talk about today is DRM, or Digital Rights Management. This is a software solution for preventing piracy and other forms of illegal distribution. This really started to take off around the 1990s and is still in use today. There are a number of different ways that we go about handling this. If you've ever been on something like iTunes or Steam, those are essentially a form of DRM. It's a place you have to set up an account, you have to purchase it, it's a one-time thing, and that purchase is applied to your account, and you generally can't take it anywhere outside of that account. Other software in the past have used access keys that you might find in an instruction manual, may have included a card, something like that. Your access to MindTap is an example of DRM. You had to have the access code or Cengage Unlimited. One very controversial example of this is constant online connection DRM, or some people refer to it as always online DRM. This really came to a head around 2013, 2014. Particularly with video games, requiring people to always have an internet connection in order to even use the game. As soon as the connection was interrupted, they were booted right out, even if it wasn't an online game. And it's things like that that have caused a lot of pushback in the last decade over DRM, because some examples of it have gone to a point where people feel like they're being treated like criminals when they legally purchased the software, because they're going through this almost prison-like system that is, in some extreme cases, even hindering their computer's performance. But they're not at their core intended to harm. It's just, we got to keep people from stealing stuff and, protect our investments, because software is very expensive to make. Some examples of different types of software, and we're going to use this chart as an example, or as a time to cover some legitimate ways that you can find software. And the first is just to purchase it from a reputable outlet. That could either be a retail store, either in person or online. It's like Walmart or Amazon. Purchasing software through reputable sources like that is a way to acquire software legitimately. You could also go directly to the source of the software, whoever created or owns it. An example of that, the drum set that I use, it's an electric drum set, and it has software that, it interfaces with software on my computer, particularly Studio One. And that is owned by Presonus. And I use the free version, which is shareware, which I'll explain in a second. But if I wanted to purchase it, I would do so through the Presonus website. Now, moving on to shareware. This is copyrighted, trademarked, patented, etc. software that is distributed for free as a trial or a partial version. And this is another thing that started to really take off in the 1990s. One of the most famous examples of shareware software is Doom. That was released back in 1993. The first third of the game was released as shareware. And as a result of that shareware distribution, Doom was installed on more computers than Windows at one point. So the problem with shareware is that oftentimes when people have gotten their fill of the shareware, they assume that they have gotten everything they can out of the entire software, and then they don't purchase it. So a lot of games nowadays and a lot of other software may not use the shareware model, or the shareware model is much more limited than it was back then. Similar to that is freeware. Again, there is copyright being held. The creator or distributor owns the rights to the software, but they choose to distribute it for free, no charge for the full version. And that somewhat overlaps with open source. Again, there are copyrights and such in place with open source, but the user has a bit more leeway with what they can do. Particularly, they have the option to modify and in some cases redistribute the software. Whereas with freeware, you can't do either. And so with open source, it has become a very popular way to distribute software, particularly from hobbyists and people generally trying to get their feet wet in the industry. They show, hey, I know how to develop fully professional software. A good example of that, a very popular tool, is Audacity. It's an open source, I believe, audio workstation. I use it all the time. I have been using it for about 10 years now, and it's fantastic. And it is an open source, again, if I remember correctly, software. And the last that I want to talk about is public domain. And this has no copyright, patent, or whatever attached to it. It has been put out there for completely free public use. And I want to make a quick distinction that that is a one-way relationship. And by that I mean public domain software has no patent or copyright. But finding software that has no patent or copyright does not necessarily mean that it is public domain. To use a mathematical term, this property is not commutative. So be mindful of that. And if you are looking for public domain things, specifically look for the phrase public domain. And I don't want to talk about software as a service or native apps. We've already talked about those more than once. So we're going to move on. Some things you may encounter when installing an application. The first is registration. This is generally optional, gives you the ability to sync across multiple devices. So say your Google account on my phone, as an example, I have all the backup and restore options set up so that anytime I switch phones, because I'm an Android user, as long as I stay an Android user, my Google account will hold all of my contacts and such. And when I first log into my new phone, all my stuff is there. And so that's the benefit of registration in a sense that I think you've all experienced at some point, most likely. Activation, on the other hand, is something that is required in many cases, either at the end of a trial period or before you can use the software at all. And this comes back to what I mentioned earlier about DRM, where you might have to enter a product key. It may be on the packaging or sent to your email address that you provided. Or it may simply require you to create an account and then have that login as your activation. Uninstalling software is generally a very easy process. Anytime you install a program, one of the things that is going to be dropped into the folder 90% of the time is an uninstaller file. And you just run that, and it will kick the programs out of your computer. If you use the control panel's add or remove programs feature on Windows, and you uninstall a program through that, it's going to search for that uninstaller and then run that for you. So 90% of the time, that's what I do. I don't go looking for the uninstaller myself. I just use the control panel. And it goes without saying that uninstalling apps frees up space on your computer. It may not delete, associated files. It may not, in some cases, even clear up that much space. But in larger cases, like if you're using Unity, if you're into game design, or if you just play games and you want to get one off of your computer, then that will free up a huge amount of space. Let's see. Software updates. This is something that everybody loves to hate, but they are a very important part of software, especially now that we are all so connected through the internet. Oops, bumped my keyboard shelf. Let me move that out of the way. So there are several reasons why updates are released. They might add new features, improve existing ones. They might address a security concern. A whole host of reasons. It could also just, make some change or remove a feature because some licensing has expired that particular component was under, and now that that's gone and they can't renew it, they have to get rid of it. But the main one to focus on is addressing security concerns, particularly with Windows updates. This is commonly why you get frequent updates. And that's why it's important to check for and install those updates to protect yourself, though I personally recommend giving a couple of days after an update has been released to install it in case something goes wrong. Because this is developed by human beings. They are not perfect. They make mistakes. And so sometimes the patches they release cause more problems than they try to solve. And once it's out in the open, people report it and they try to fix it. And that's why I generally recommend waiting a couple days. In some cases, updates can be installed automatically, and with mobile devices, that is the standard typically. Like, I don't usually go out of my way to check for updates on my phone. It just does it. Sometimes it needs manual action, in which case it'll tell me. Excuse me. Native software, again, not going to go into detail on this. Non-native, again, no. What I want to focus on is troubleshooting. And we're going to go over this in a sort of live demonstration later. But for now, I just want to talk about the steps. So we've probably all had this happen where a program seems to be running just fine, or something seems to be amiss for a moment, and then the program crashes. What do you do? First thing to do is to, in the event of a crash, take notes. Look and see what kind of error you're being given. Oftentimes, it's just, this program has encountered a problem and needs to stop, and that doesn't tell you anything. Other times, it might tell you out of memory, or it might give you some error code. And it's important to write that down in case it repeats. To protect yourself in the event of a crash, the main thing you want to do is save your progress frequently. Once you have gone through the save as option of any given software, From that point on, as long as you're working on that same file, just hold Control, press S, takes a quarter of a second, if not less, and it will save your progress for you. Be sure to do that frequently so that if it crashes, you don't lose much. And now some steps to deal with the problem directly. The first thing is just restart the program. Sometimes it's just a fluke. Something didn't get sent over to a particular process correctly, and now the program doesn't work anymore and it crashes. In most cases, restarting the program will be enough, and you can just go about your business. If it continues, you can try rebooting your computer and running the software again. Checking for updates. This can be a Windows update, an update to the software itself, its distribution service, if it has one that you had to install on your computer, such as Steam or iTunes. Or if it is a software that relies on a graphics card, again, games or development software, you would also want to check your graphics drivers, make sure they're up to date. So generally, make sure your stuff is up to date if you're encountering a lot of problems. I'm going to skip the next step over because I feel that is something that should come after scanning for viruses or malware, because these can interrupt program operation. They might hog up machine resources and cause things to not be written to memory correctly. When you have your notes together, you could search a reputable source, such as a tech forum or something along those lines, to see who else has encountered this problem, what they did to fix it. I would recommend not using something like Reddit because, you know, the information, it might be helpful, it might not. You are taking a huge gamble by going to Reddit or something like that. Go to something like Linus Tech forums or something like that. I've gone onto there several times and found helpful information. There may also be, you know, journal articles about it, newspaper, magazine things that you can use. Just make sure the source that you're looking at is reputable and they're not feeding you a bunch of garbage. Otherwise, you will end up doing more harm than good. Just as an example, I don't know if you guys remember this, all the fuss about the one particular iPhone model not having a headphone jack, and people were saying, oh, it's hidden under the case of the phone and all you need is a drill. And so people drilled into their iPhones and destroyed them, thinking they were going to get at a headphone jack. And it's an unrelated to troubleshooting, but this is the first example of, you know, why you should look for reputable sources that I could think of. And a last resort to dealing with a crash is to uninstall and reinstall the application. Should be a quick process in most cases, but I would still treat this as a last resort because it may change some things on your computer that the software relied on, and you might have to go in and fix those. Some troubleshooting tools. I pretty much only use Task Manager myself. I've shown you guys how to access it, very quick and easy to get to. It is your process manager and it is your system information list. It will show you everything that's going on your computer in detail. And if a program is flagged as being non-responsive, you could just force it out of memory through Task Manager. But as far as auditing tools, patch finders, and restorers, I have personally never used those. I haven't had to. And I would encourage you to read more in depth about them in your textbook. All right. And we're moving from software to its development. And before we dive into this, does anybody have any questions?
No.
All righty. And for some reason, this starts off by talking about licenses. You have at some point seen an end user license agreement or EULA, and those are single user licenses, but there are also multi-user licenses as shown here. I don't want to spend too much time on them, so just read up on them in your book. And now we're going to get into some programming concepts. I'm not going to show you any code or anything like that, because since we're already doing this, I don't want to overwhelm you by adding in the other. And also, you voted no. You guys voted no on it. But I will talk about object-oriented programming here. And what this is a concept that began around the 1980s as code was getting so large because there was no way to reuse code. It was getting so large that programs would be increasingly unlikely to succeed in their development as they got larger to a very infeasible degree. And so object-oriented programming is one of the solutions that addresses this. And what it does is it is a framework that represents real-world objects in code in a logical fashion. So everything you can think of in the real world has properties, has some sort of characteristics, and it also has things that it can do. And so with object-oriented programming, we have distinctions made in code for those. And we call the properties or characteristics members. We call the things that they can do, their behaviors, we call those methods. And these are lumped together into a class. And this class is a definition of the object containing all the information needed, but no specific inputs. When we create an instance of that class that lives in our program temporarily and contains its own unique set of inputs, we call that an object. And the reason, again, why we have object-oriented programming, not only is it because it allows for code reuse, which makes development much easier, faster, cheaper, it also makes code much easier to understand, because we can all understand that a banana is yellow and you can peel it. And so we can represent this in code using OOP. What else? Something that isn't mentioned here. Principles of object-oriented programming. I'm not going to go into detail on all of them because it is complex and requires you to have an understanding of programming, which I know not everyone in here does. But the main one I want to focus on is inheritance. And this is one of the most powerful features of any language that supports object orientation. What this is you can specify a class as being the descendant of another class. So you might have a general class called fruit, and then from that you have a child class called banana. And in this case, we have an is-a relationship. That is to say that banana is a fruit. And that works, verbally, it works logically within the program. And so that is one of the major advantages of OOP, is when you define that inheritance, everything that was defined in the parent class is inherently added to the child class. It is there from the word go. Some design guidelines that we follow when we are designing programs. Obviously, what kind of devices it'll run on, what operating systems, does this require a server, is it mobile, etc. Exploring capabilities of languages and tools. Different programming languages are better suited to different things. Certain development tools are geared towards specific kinds of development. Performance considerations, how fast do you want the program to respond to inputs, and the type of environment the program offers. Is this a productivity suite? Is this are we creating a programming interface? All considerations that have to be made in addition to the usual business things of man hours and cost. And here, again, talking about the different kinds of software. We've discussed this in detail before. And now we're going to talk about the methods for developing software. Within a software development team, there are several roles, and these are going to sound very familiar with any other kind of development team, such as construction workers. So at the top, you have the project manager who coordinates between everybody, keeps everything on track, is essentially the group leader. It would be like your general contractor or your foreman. The designer is the one who draws up the specifications. They might do tabletop prototypes or sequence diagrams. I'll explain what those are in a minute. They don't necessarily write the code, but they give the programmers who do write the code a very clear idea of what needs to be done. So if you are in computer science, just to give you an idea, you will be playing the role of the programmer in Software Engineering 1, that's CS310, and you will be taking on the role of the designer in Software Engineering 2, that's CS491. You will be exposed to the software development process after you've built some coding skills. And there's a good chance that you may end up in the project manager role, depending on how your instructor decides to break up the class, particularly in Software Engineering 1. User experience. This is a crucial part of software development at all stages, from the beginning to the end. And this defines how the user is going to interact with a piece of software, and how we can go about making it as helpful to them as possible. There is an entire class dedicated to this. You could probably make an entire degree concentration out of this. I could not even begin to scratch the surface on everything associated with user experience. There's a lot of psychology and sociology associated with it. Again, if you are a CS major, there is a human-computer interaction class.
I can't hear anything. Is he just gone?
Hello?
I just couldn't hear you for a minute.
For some reason, my mic muted.
Oh, okay.
Okay, hold on just a moment. Let's get back into this. Where did you stop hearing me?
Alec, right there. You were saying something about there could be a whole degree in this
In
thing.
UX? Yeah, okay.
Yeah.
So, yeah, all I was about to say is there are a number of things that we take into consideration when we are designing around UX. And one of those is that we take every single interaction and we divide it into what we call a sequence. And for any given program, this could be dozens or even hundreds of diagrams. Every single sequence gets its own diagram, which is just a linear representation. I was struggling to find the word. A linear representation of how the user gets from point A to point B within a particular type of interaction. There are also things like color palette to consider in the event that somebody has visual limitations like myself. You might need to consider higher contrast colors or larger fonts. Little things like that, all the way up to bigger things like how the entire program is laid out to make sure that everything can be found pretty easily. And yeah, like I said, there are classes on this. There is a human-computer interaction handbook that talks about this that, I'm not kidding you, is about the size of the Bible. It is enormous, and there's a ton to talk about. All right. Now moving on to methodologies. There are a number of different ways that we go through the software development process. The first of these is predictive development or linear development. The most famous example of this is the waterfall method, in which we start from the beginning, we go to the end. It is as simple as can be, and it often doesn't work in terms of software, because new information becomes available, and now we have to integrate that information into our software design. So we've developed more cyclic approaches, and some of these might just go through the entire process and then loop through it over and over again. Some will loop through part of it and then go back. And others will go part way through and then circle back to another. Like, say you're at step 7 and you loop back to step 3. Other things like that. There's a whole bunch of different design methodologies. I'm trying to generalize and not go too in depth, because this is another area where there's a lot of study being done. But one of the more interesting things that I do want to touch on is agile development. This is something that is covered in Software Engineering 1, and you have, pardon me, the way it works out, you have a small team, and in some methodologies, this is called a scrum. This scrum consists of somewhere maybe 6 to 8 people, maybe a couple more, maybe a couple less, but is generally a very small team. And in agile development, they are given small projects to take on. And when you form up your scrum, you take this small project and you break it up into bite-sized pieces called sprints. And each sprint is going to be focused on for a month at most. usually it's like 2 weeks. And you're going to work on this particular feature for that 2 weeks in a very fast-paced, very, if you fall behind, you're behind sort of setup. And at the end of that sprint, things are reviewed, lessons are learned, and whether or not that feature is finished, you move on. If it is not finished, it goes back into the pile to be done in another sprint. Agile has gained popularity over the last several years. I've already mentioned Scrum. There's also Extreme Programming, or XP. A lot of businesses have adopted it. And for that reason, you're going to see it if you're a computer science major in CS310. But regardless of which methodology you're using, you will always go through these 5 steps in some order or another, usually in this order, but with backtracking in mind. And so we begin with the planning phase, and this is where we decide, okay, what do we need in order to make this? And also, what are we making? What kind of staff do we need on this? What kind of machines, software, room space? What features do people want to have here? Can we do them? And how much is this going to cost? That is your planning phase. Your analysis phase. This is where you start to really draw up your requirements for the software and put together your proposal. And this is where you're going to be introduced to functional and non-functional requirements, which sounds very strange to me, but once it was explained, it made perfect sense. So the difference between functional and non-functional requirements is that functional requirements have to do with how the software runs, what can be coded into it. Like user presses this button and they're presented with a form to submit an entry to a database. That's an example of a functional requirement. Whereas a non-functional requirement is more along the lines of, what laws do we have to design around? What are our privacy concerns? Things that can't necessarily be programmed, but do need to be incorporated into the software. Next is your design phase, and this is where you are going to write up things like your sequence diagrams, also your database schemas, your flowcharts, everything that explains how the program is going to run. And you may also generate a prototype of some kind. It could be programmed. It could be just a tabletop demonstration or a PowerPoint or something like that, just to show this is how the software works. And all of this we have done. We have gone through 60% of this, possibly without touching a single line of code. That is where step 4 comes in. That is implementation. And this is where you write all your code. In computer science, you will learn that programming is the easy part, because there is all this coming before it that just flat out tells you exactly how to write the code, assuming it's written well. And obviously, as part of implementation, we test the software, verify that it works. We install it where it needs to be, and we train people who are going to be using it. This could involve, a training session on site with the company. It could be writing up a technical manual if this is a commercial piece of software. Giving the IT department the necessary steps to help customers troubleshoot problems, and so on and so forth. And then the final step is support and security. This is where we monitor our programs for any sort of issues that might arise, whether they be performance related or security related. and we take all this into consideration for potential updates. And those updates bring us right back around to step 1. And all of this we call the software development lifecycle, or SDLC. And there are specialized variants of this throughout different concentrations of computer science. Database systems have their own life cycle that involves 1 or 2 more steps. But in general, all variants of them follow this same circle. All right. Now on to tools and strategies, the last thing we're going to talk about today. The types of programming languages. First off, there are way more here than any of us are ever going to learn in our lifetime. There are hundreds of them. There are a lot of similarities between them because they all have to communicate in a similar fashion, but all of them serve different purposes. They are different levels of cryptic. That's the only way I can think to put it. And so going from the most basic to the most complex and readable, our low-level languages are ones that are more read by the computer. And one of these is machine language. Essentially, this is binary, formatted in different ways so as to directly reference addresses in memory, whether that be the cache, RAM, or registers or something else like that. Going up from there, we have assembly languages, and these also will directly reference, but you can think of this as a sort of labeling for machine code. It's something that's more easily read, still very difficult to read, in my opinion. I have worked with assembly code before, and it makes absolutely no sense to me. My home is procedural languages, and these are more plain English. They use real words like if and for, and the language, the phrases we were using up above in object-oriented programming, you'll see those used directly in code. And finally, one that I didn't really know about until now, 4GLs, or fourth generation languages. These are procedural languages in and of themselves that are more plain English than even procedural languages. These are made to be more easily understood. An example of 4GLs that I do use, just didn't realize it was a 4GL, is SQL. We mentioned this before in talking about databases. But yes, according to my sources, SQL is an example of a 4GL. Some specific programming languages. These are all procedural, and by far procedural languages are the most popular. So beginning with a common ancestor of procedural languages, C. This began in the 70s. It's been around for almost 50 years, but people still use it. It has given way to C++. This is a very powerful language that helped to popularize object-oriented programming. And for those of you who are interested in game design as a career, C++ is absolutely essential. Most game engines use C++. So if you are interested in game design, then before you leave JSU or get your degree, whatever, you need to master C++. It is a difficult language. I'm not going to lie to you on that. But it is extremely powerful, extremely optimized, and used by most game developers. C#, is yet another C variant, obviously. This is Microsoft's own app development language. You find it commonly in use with web applications. And speaking of the web, HTML is the backbone of all websites. You notice, oh, excuse me for 1 second, that a lot of website names might end in .html. That is because you are looking at an HTML file being read by your web browser. And if you are going to get into web design, you will start here. There's no other way around it. You're going to start with HTML. It is going to define exactly the shape of your web pages. You're also going to learn JavaScript. This is a popular web application language, good for interaction on websites as well. Very easy language to learn. So again, if you want to get into web design, I would put at least some degree of focus on that. You've also got PHP, another web language for storing, retrieving, and representing data. And finally, as far as web languages go that I want to talk about, excuse me 1 second. As far as web languages go that I want to talk about, Python. This is not exclusively a web language, and neither is JavaScript, but commonly used in web development. Python in particular is used for a lot of data mining and artificial intelligence and what else? I'm sorry, my mind just went for a second. Scientific calculations and such. We've had a professor here who's been working on converting some old statistical analysis software to Python for that reason. And it's also just generally a very easy language to learn. If you are completely new to programming, Python is a good place to start. As much as I have my own criticisms for it, I can't deny that. Java is another easy language to learn. It is entirely object-oriented, whereas C++ and other similar languages allow it. Java just is object-oriented 100%. Oh, let me turn off my alarm. Moving really quickly to finish up. I don't want to go into too much detail about these other three languages here. Just know that Swift is the iOS development language. And we've already talked about SQL. Last slide here is talking about the different tools you might use. You have a code editor. You can use something simple like a text editor. I use Notepad++, very handy. But all it is a text editor. You want to use plain text and not rich text. So don't write code in Microsoft Word that's not going to work. You also have debuggers, which will look through your code and check for any errors that might occur. Compilers turn your code into an executable program. It might be an exe file. In the case of Java, it's a .jar. Interpreters will read code and execute it on the spot. And that brings up an important point. The difference between compiled and interpreted languages is exactly what I just said. There's compiled languages are made into standalone programs that don't require any other software, whereas interpreters do require the software associated with the programming language. So Java is kind of a weird mix of both, in that it creates something for the interpreter from code, which is itself compiled. It's strange. I have a hard time wording it and understanding it, but all I know is Java's good, and it requires the Java runtime environment. And all this seems complicated. All of this, like, why do I need 4 programs in order to do programming? The answer is you don't, because we have programs that take all of these and put them together. We call them IDEs, or integrated development environments. For C++, you might use Visual Studio or code blocks. I prefer code blocks myself, but Visual Studio does admittedly look a lot nicer. For Java, most people use NetBeans. And these will take, all the programs that we're talking about here and wrap them up into one neat package for you. And finally, the point I want to make a quick point about code repositories. We've mentioned cloud storage before, but this is a special type of cloud storage that includes some specialty features for managing versions of your code, merging changes across multiple users, allowing people to make their own version by making a fork of that software. The most popular example of this is GitHub, but there's also Subversion and others available.